Can you hear me?
Yes, awesome.
Always a good start. Okay, well, firstly, thanks ever so much for inviting me. Nothing more fun than visiting Birmingham during a bin strike. As mentioned, I run a little place in Wales called the Spaceguard Centre, where we do astronomy, but not ordinary astronomy. We're really not terribly interested in stars, galaxies, that sort of thing. Our focus is on planets, but not the big ones. It's the little ones that we play with, and we've got 15 or 20 billion of them, so we're not really short. However, it is quite a new subject, and really it shouldn't be. It's new because we made a mistake. And in science, of course, that's pretty common. It's how a lot of science works. But this one dates back to Isaac Newton. Isaac Newton, bless him, back in 1687, told us that our solar system, I promise no sound, in fact, the universe as a whole was mechanical, predictable, peaceful, nothing ever changes, just like God made it. But a century and a half later, along came people like Hutton, Lyell, Darwin, who told us that things do change, but they only change very gradually, over hundreds of thousands or millions of years. And really, all of that finished off the old idea of sudden catastrophic change. In the good old days, they knew jolly well that every now and again something big and bad comes along, changes everything. But that idea was really left to the ignorant and superstitious until we went into space. Because when we had a close look at the other planets, we began to realize that the old guys might not be quite as wrong as we thought. Well, when we had a close look at the other planets, we began to see things that we really didn't expect to see. For example, this is what the surface of Mercury looks like, covered in craters. If you go out to Venus, that one's covered in craters. And if you go the other way, out to Mars, same detail. But of course, once you get beyond Mars, the planets aren't solid, just big gas giants, and you wouldn't expect that sort of thing on a big ball of gas. But that's what Jupiter looked like back in July 1994, just after it was hit by a whole series of comet fragments. The dark smudges you can see at the impact sites, just dust lying on the cloud tops. But when that happened, everybody thought it was a once-in-a-lifetime chance to see something actually hitting a planet. And it was, until the summer of 2009, when it happened again. On this image, taken by the Hubble Space Telescope a few days after this was discovered, there's a big dark smudge. Turns out, the behavior of the dust is precisely the same as what we saw back in '94. So Jupiter was hit again. And again, the following year, a number of people saw that huge flash, bottom right. It only lasted a couple of seconds, but the fireball was about the size of the United States. Since then, we've seen a few of these. This one, for example, back in 2019. One of the really fun ones, though, happened just a couple of years ago. Boom. But if you look at the moons of the gas giants, which, of course, are solid, then we're back to square one. That's one of Jupiter's 95 moons called Callisto. If you go out to Saturn, you'll find a nice little moon called Mimas. The thing that made the big crater there was almost big enough to smash the moon to bits. Go out to Uranus, and even as far as Neptune, and you'll still find moons covered in craters. So everywhere you look in the solar system, everything's been battered to death. With one big exception. And people used to think that for some completely unexplained reason, the Earth had just got away with it, until we started looking at the Earth from the outside. That's when we realized we got that one wrong. Nowadays, wherever you look on the Earth, we're finding craters. We've got just over 360 in the catalogue at the moment. But when people started finding lots of these, it seemed to come as a great big surprise. And why anybody was surprised, I'm not sure, because all you've got to do is look at the next door neighbour. We share the same bit of space with the moon, so the hit rate there must be a pretty good indication of the hit rate here. We've got a group in the United States who watch the moon just to see if they can see anything hitting it. Well, since they started back in 2005, they've seen quite a lot. So things do hit planets, no doubt about that one. It's just that when they hit, if they're big enough, everything on that planet changes very quickly. So we seem to have a little bit of a problem. Things hit planets and we live on one. And that really leaves us with three quite important questions. Firstly, what's doing the damage and why? We also need to know how often it happens, because then we can decide what to do about it. And thirdly, is there anything we can do about it? But the first of those is what's doing the damage. And the best way to find out about that is to find out where all this stuff came from in the first place. Our planets formed in a disk of material that orbited around the young sun, and over time, the little bits of dust and so on began to clump together and grow, eventually forming the planets as we know them. In our particular planetary system, we've got 8, 4 little ones, 4 big ones. But there should be another. In between the little ones and the big ones, there's a socking great big gap where there should be another planet. And it's not there. What we've got instead are all the little bits that should have clumped together to make one. Happened everywhere else, but it didn't in that gap. So, in that gap, we've got millions and millions of big lumps of metal and rock. We call them asteroids. The other group, I've got to show you a picture of an asteroid. There we go. And there's actually quite a lot of these. This is a recent plot. All the little green dots are in that main asteroid belt. The ones in red, on the other hand, have orbits that cross or nearly cross the Earth's. There's another group of objects that we're looking at. If you go out way beyond the realm of the planets, out into what's called the Kuiper Belt, which then spreads out into the Oort cloud surrounding the whole of the solar system, we find the bits that were left over when the sun formed. Big lumps of ice and dirt, big dirty snowballs, if you like, which is the standard model for a comet. So, between the terrestrial, small rocky planets and the gas giants, we've got asteroids, and way out beyond the planets, we've got comets. They're unstable, though. These things are small, so their orbits around the sun can change. They can be perturbed quite easily. Some will head away from the sun, but if they're heading towards it, then the planets can get in the way. And that's when we get hit by stuff. Now, asteroids, fairly straightforward, lumps of metal, rock, other things as well, including water ice. But the comets are perhaps a little bit more fun. Most people seem to think that comets look something like that. Big, fluffy things, long tails, and so on. Sadly, of course, that's not what a comet looks like most of the time. That's what a comet looks like. It's a big lump of ice and dirt with a skin on the outside made of stuff rather like tarmac, a sort of tarry organic residue. But if one of these moves towards the sun, it warms up. And when you warm up ice, it changes. What it can't do is melt. You can't have liquid water unless it's under pressure. Space is a vacuum, so liquid water can't exist in space. So the solid ice turns straight to gas. It literally boils before it melts. Sublimation. But as soon as that starts, it's like trying to blow up a balloon. The pressure on the inside of the skin builds up until eventually, where it's weak, the skin will crack. And when it cracks, you get little jets of stuff coming out the comet. Gravel, dust, gas. In fact, not long after the Rosetta spacecraft reached this fella here, he started jetting. Some of that stuff will fall back down. That'll help to thicken up the skin. But most of it forms a massive cloud right round the whole thing. And when all of that gets even closer to the sun, the solar wind begins to blow that cloud away, forming the tail. So the tail's being blown away by the sun, so it always points away from the sun. It's got absolutely nothing to do with the direction that the comet's moving in. If you look carefully at the stars in the background there, you can see that comet is moving that way. But what the tail tells us is that comets are unbelievably grubby. Tempted to say that this is the solar system's equivalent to the teenager, but I see I'm outnumbered. Wherever it goes, it's leaving a trail of dirt and debris. But every now and again, as the Earth whistles round the sun, we go through one of those trails. And that's when you get a meteor shower. So your average shooting star's just a tiny piece of coal burning up in the upper atmosphere. Normally about the size of a grain of sand, burning up 15, maybe 20 kilometers above the ground. So shooting stars are totally harmless. But if we up the game a little bit to a bit of asteroid or comet, a few tens of meters across, small house up to reasonable sized mansion, that's not going to hit the ground either. What it will do is it'll pop in the atmosphere before it hits the ground. Airburst. Now, back on the 30th of June, 1908, a little lump of asteroid, about half the size of a football pitch, came whistling in over eastern Russia. Just over the Tungus, in the Krasnoyarsk, when it was still 5 miles above the ground, it popped. The explosion was about 1,000 times more powerful than the atomic bomb dropped on Hiroshima. The heat and the blast completely shredded the forest underneath. Just over 800 square miles. In fact, it was exactly the same area as the Snowdonia National Park. And again in 1930, this time in South America. This one was probably about half the size of the Tunguska event. But you may well be familiar with the famous Chelyabinsk event back in 2013. This one was really quite small, only about 17 meters across. Came in at a fairly shallow angle and eventually popped 22 kilometers above the ground. The explosion was about 20 times the Hiroshima bomb, picked up by dozens of dash cams, CCTV cameras, all sorts. Luckily, it was too far from the city to do any real structural damage. The real problem here was glass. It's 122 seconds from the flash to bang. Plenty of time for people to realise something's going on, go to the window to have a look, and off we go. So most of the 1,600 casualties here were caused by flying glass. But this sort of thing's really not that uncommon. It's rare for it to happen near a city or a populated area, but recently the Americans have published their data on these airburst events. They've been picking them up for decades. But these are all relatively small. If we up the game a little bit further to something about 150 metres across, football stadium size, that will hit the ground, and it'll hit the ground at about the same speed as it had been travelling through space. The atmosphere simply doesn't have the time to slow it down. But when a thing like that hits the ground, it's not going to stop. It's like firing a bullet into the ground. It'll keep on going until the ground physically stops it. But when the ground stops it, the comet or asteroid blows itself to gas. So what you get is a nice big explosion just under the ground, which blows a big hole in the ground, and it's that hole that you see as the crater. It's also why nearly all meteorite craters are perfect circles. People used to think that if something came in at an angle, you get an oval shape. Actually, it really doesn't matter what angle it comes in at, because it hits, keeps on going, stops, then it blows. 150-metre sized object, that'll blow a crater about 3 kilometres across. Craters are normally about 20 times the size of the thing that did it. The immediate effects of that would take out a small country. Belgium, Holland, something along those lines. But that, of course, makes it local, easy to recover, because people from the outside can come in and fix everything. So the really tricky one is when we get a global problem. To do that, you need a comet or asteroid about 1 kilometre across, 2/3 of a mile, blowing a 20-kilometre sized crater. But within a few hours of that, the effects will be global. And there's a whole catalogue of things that start going quite badly wrong. What you're not looking at, though, is sort of end of days, mass extinctions, anything like that. We're not even close. We'd expect to lose somewhere between 20 and 25% of the human population of the planet, a couple of billion, give or take, but that's easily recoverable. The really tricky bit is with the clever stuff, the technology that underpins a modern civilization. That'll fail. So the survivors are going to have to muddle through without power, communications, transport, central authority. To all intents and purposes, they just slip back into the Middle Ages, sort of feudal agricultural system. Cities, for example, they'll be abandoned. There's absolutely no point in being. But what you've still got are all the resources you need for recovery, physical and intellectual. So hopefully, after a period of time, perhaps a decade or so, civilization can begin to reboot again. So if we get this right, it is recoverable. What's not recoverable are mass extinctions, and we would expect those to kick in with objects bigger than about 5 kilometres across. And from then on, you just ratchet up the size of the object and the extent of the mass extinction. The famous one, of course, was about 10 kilometres across. Blew a nice big 200-kilometre sized crater in what's now Mexico. But within a fairly short time at that, probably only a matter of months, about 70% of all the species of plant and animal on the planet were extinct. Logically, we could envision something big enough to simply sterilize the entire planet. So, just to recap, something about 50 meters across. The airverse produced by that would take out a reasonable-sized city. 150 meter takes out a small country. 1,000 meter, then we have a global problem. And 5,000 and above, then we are seriously looking at mass extinction events. This we know. What we do need to know next, though, is how often does this sort of thing happen? And the best way to find that out is to find out how often it's happened before. And that we can do. We know how to identify craters, so all we need to do is count them. Somewhere where there's no atmosphere to get in the way, no water, no weathering, but still reasonably close. And that one's easy. We've got the moon. And it's the lunar crater count that's allowed us to put together a fairly robust frequency table that tells us how often we get hit by different sizes of objects. Before you groan, this is the only graph I've got. But if we look at the big fellas, mass extinction events, we're looking in terms of millions up to hundreds of millions of years. Seriously not something to keep you awake at night. But if we go down to the ones that do global damage, we could be looking in terms of a few tens of thousands of years, maybe 100,000. But even the 100,000, that's, on the timescale of a normal civilization, really quite significant. Go down to the ones that would just take out a large city, then we're looking in terms of years or decades. But once we'd realized how much damage these things can do, and how relatively frequent they are, we began to look for ways of stopping it happening. And that, at least in principle, turns out to be fairly straightforward. The first step is to find any potentially dangerous asteroids or comets as long as possible before they actually become a problem. When you find one, you need to know where it's going, so you have to track it for a period of time. And when we find one that's coming, it would be nice to have some method of making it go away. But the first of those is the finding bit. Now, finding asteroids can be a little bit tricky because through a telescope, an asteroid looks precisely the same as a star, just a little point of light. But thankfully, the asteroids, comets, and ourselves, we're all members of the solar system. And everything in the solar system orbits round the sun. So all solar system objects appear to move relative to the background stars. So in effect, we're looking for a moving object. In the old days, you would take a long exposure photograph and look for a streak where something had moved while the picture was being taken. Nowadays, with better cameras, you take a number of short exposures and look for something that changes position between the frames. And all of this was made so simple back in the middle of the 1990s when these little fellas showed up, the CCD imaging chip. Prior to that, it was all on film. But at the same time, we had those impacts on Jupiter, which really should have made the world sit up and realize we might have a bit of a problem here. As it turned out, it was the United States that woke up. So Congress told NASA to find 90% of the big, potentially dangerous asteroids. That's kilometer-sized or bigger with orbits that cross or nearly cross the Earth's. The best estimate at the time, there'd be somewhere between 1,000 and 1,100 of those. So NASA put together a group of telescopes to conduct the search. This is just some of them, mainly, of course, in the United States. But we did have one search program in the Southern Hemisphere at Siding Spring in Australia. At least until 2013, when the Australian government pulled their half of the funding and this one shut down. But by then, NASA had achieved that 90% of the big ones. Right now, somewhere between 96, 97% complete. So Congress told NASA to drop the size, go down to 140 meters. And that's a whole different ballgame. They're much harder to see because they're smaller, and there's an awful lot more of them, 25 to 30,000. So, while the original telescopes are being upgraded for the new phase of the search, a number of other instruments joined the game. This is the LINEA program in Socorro, New Mexico. We've got Spacewatch on the top of Kitt Peak in southern Arizona, the Catalina Sky Survey just outside Tucson. But the real king of the game right now is Pan-STARRS, Joint United States Air Force University of Hawaii program, using two identical telescopes on the top of Haleakala on Maui. To help out with that gap in the Southern Hemisphere, the United States Air Force moved their big space surveillance telescope from New Mexico to the west coast of Australia. And at about this time, a number of other organizations, countries, thought it might be quite a good idea to join in. Now, perhaps the most significant of those was the European Space Agency. So much so that ESA has set up its own Near-Earth Object Program now. It runs in parallel with NASA. But when it comes to the search, the real game changer is going to be this one. This telescope's not quite finished yet. It should have been finished at the end of January, but big engineering program, always going to slip a little bit. So now we're looking towards the end of May, but it's certainly going to be big. The primary mirror on this telescope is 8.4 meters across. In fact, that's the mirror before they started to polish it. Now, since then, polishing's complete. They've shipped the mirror up to the site. In fact, last October, they put the final reflective coating on the mirror. This is it coming out of the vacuum chamber, having been silvered. That, I would suggest, is a thing of beauty. But combine that with the biggest digital camera ever built. For the nerds amongst you, 3.2 gigapixel camera. This thing's going to find shells of asteroids. Not that that's what it's designed to do. It's designed to scan the entire visible sky from its site in Chile every 3 days. It's looking for things that change. But while it does that, it's going to find bucket loads of asteroids. Now, until last September, we also had our hands on a space telescope, the Wide Field Infrared Survey Explorer, originally launched to map the entire sky in the IR. Well, it did that. And when it was finished, it was handed over to the Near-Earth Object Program. We used that for the best part of 10.5 years. It was certainly beginning to show its age, but the real nail in the coffin for WISE was the fact that its orbit round the Earth was decaying very quickly. So back in September, NASA bit the bullet and finally switched it off. But in 2027, it's going to be replaced by the Near-Earth Object Surveyor, another infrared space telescope, but this time specifically designed to look for asteroids. So in fact, we've already got all of the technologies that we need to find these things, both ground-based and space-based. Unfortunately, all of the instruments I've mentioned so far are really good at picking up big objects some distance away. What they're really bad at is picking up the much smaller objects that we only pick up when they're close. And that's because when they're close, they appear to move really quite fast. So, to solve that problem, the United States have developed their Atlas program. 7 of these dotted around the world, specifically designed to pick up those small, fast movers. Europe hasn't been left behind because ESA has developed the Fly-Eye telescope system for precisely the same thing. Point is, if we wanted to, we could find these things. The next bit, though, is working out where the darn things go. Now, luckily, that's a problem for the mathematician to calculate the orbit round the sun. But the first thing we need is a distance to that little white dot on the photograph. It's only two-dimensional. Could just as easily be a big one some distance away or a much smaller one closer in. But thanks to the laws of physics, the closer to the sun you get, the faster you move. So over a period of time, those 3 virtual asteroids will move different distances. All you have to do now is make another observation, and you can begin to narrow down the distance to the target. Which means, of course, in this game, certainly initially, we don't deal in certainties. We deal in probabilities. Carl said, for example, next time round, that fella there is going to fly through that point in space. Or you can say, it's a little fly through an uncertainty ellipse. But if the Earth is in that ellipse, we've got a measurable hit probability, albeit quite low. But as time passes, more observations are made, the ellipse gets smaller, but if the Earth's still in it, that hit probability is gone. More observations. The ellipse gets smaller yet, and the Earth pops out. Now we have 0 hit probability. And that's how it happens nearly every time. Start with a low hit probability that gets higher and higher, and then straight down to 0. And the tabloid press simply can't get their heads around that one. You might have heard, earlier on in the year, we had a bit of a spat over a little asteroid, 2024 YR4. Started with a very low hit probability, got higher and higher, quite alarmingly high, and then, as predicted, straight down to 0. In fact, this is the hit probability graph for YR4. As you can see, gets really quite hard, and then, as expected, straight down to 0. Leaving the Daily Fail and the Sun with egg on their faces yet again, I'm afraid. But that's how it works. Nearly all of the observations you need to do this sort of work are made by amateur astronomers, which is absolutely fine. They do a cracking job. All of their data, along with all the data from the professional search programs and so on, is all sent to the Minor Planet Center, currently located in the United States. This is the global hub for all data relating to asteroids and comets. It's also where they do all the orbit calculations and so on. But it does mean that we have a system in place to track these things as well. So we can find them and we can track them. The next bit, though, is what to do when we find others on the way. Before we can even consider what to do, we need to know a great deal about the target. We need to know what it's made of, how big is it, how fast is it spinning, and so on. And over the last 20 years, we have visited a large number of asteroids and comets to find out what they're made of, how they're put together, and so on. We don't have all the answers yet, but we're certainly well on the way. We've even been and picked up bits and brought them back. This is touch and go with the Japanese Hayabusa spacecraft, visited a little asteroid called Ryugu, touched down, picked up bits, and brought them home. The Americans did exactly the same with their OSIRIS-REx mission. This is their touchdown, and again, picked up bits and then brought them home. In fact, for those of you with a morbid interest in this sort of thing, those are some of the bits. So, we're beginning to find out what the physical properties of these things are. Once we've established what the physical properties are, then you can come up with a reasonable plan on how to stop a potential collision. And really, it all boils down to three options. The first option, the British option, is to do nothing at all. Just sit back and hope it all goes away, preferably with a cup of tea. Sadly, of course, that's not going to happen. So, moving on. The second option is to go for the sort of Hollywood approach. Let's try and blow the thing to pieces. Well, that's absolutely boring. Just depends how stupid you want to look at it. Because all you've done is turn the predictable bullet into an unpredictable shot down last. So in effect, that one's off the table. The third option is simply to turn a direct hit into a near miss. Give the object a tiny little nudge, just enough to guarantee it misses. Now, quite how you do that, as we've mentioned, is going to depend on a huge number of different things. Does mean that there's no silver bullet here. What you need is a folder full of different deflection methods to take on different types of target. And that is precisely what NASA's Planetary Defense Organization and the European NEO SHIELD project are looking at. They're looking at things like kinetic energy. You literally just bang something into the side of the object to push it, of course. You might remember a couple of years ago, NASA did precisely that with their DART spacecraft. They targeted the smaller of a binary pair of asteroids. The little one orbited round Trinary in 11 hours, 55 minutes. The aim of the game was to slow it down by at least 73 seconds. As it turned out, we slowed it down by 3 minutes and 20 seconds. Worked really quite well. In fact, this is what it looked like from the ground, the impact. So, we have tried the kinetic energy method. It works, but not suitable for all types of target. You may decide to go for a process called ablation. The idea here is that you heat up one particular spot on the surface, it'll vaporize, the vapor jets outwards, producing thrust in the opposite direction. A slightly cruder way of doing that is the nuclear option. You pop your device some distance away from the object, and it's the heat and the radiation that ablate the surface. Very simple, very quick, very efficient. But perhaps the most elegant way is to use gravity. Park a spacecraft next to the asteroid and edge the spacecraft away. The mutual gravity between the two will tug the asteroid in the same direction. Not much, but if you think how small a target the Earth makes, quite enough. And almost certainly, if we've got the time, that'll be the method of choice. So, we can find them, we can track them, and we can make them go away. And just recently, the United Nations has finally got involved as well. We have now a structure at the United Nations to address all three stages of the process: find, fix, and neutralize. But there is one little elephant in the room. We have observed on a number of occasions in the past large comets that have fallen apart. Comets, big dirty snowballs, they're very fragile things. But if a large comet does fall apart, it's going to produce a mass of big bits, medium bits, and little bits. And the family of comets that we're particularly concerned about at the moment are called centaurs. These come from the outer reaches of the Kuiper Belt or Oort cloud, moving in towards the sun, captured by the gravity of Jupiter and or Saturn, and there's a big blob of them between Jupiter and Uranus. But their orbits are wildly unstable. If one of those should approach the sun and fall apart, then we do have a bit of an issue. The orbit of that object is going to be absolutely saturated with, as I said, big bits, little bits, and tiny bits. And if the Earth passes through that cloud or that trail, we can expect large numbers of Tunguska-sized events popping all over the place. We could expect the dust to enter the atmosphere, literally fill the sky with shooting stars, set the sky on fire, which will in turn ignite pretty much anything that's flammable on the ground underneath. Bigger bits, well, they speak for themselves. All of that's quite dramatic, but actually probably the real killer will be the dust. Once it settles in the top of the atmosphere, it will literally block out the sun for months, years, even decades. People often talk about nuclear winter. Well, that would be an absolute doddle compared to this. So the centaur problem is one that is just beginning to bubble out now. Nobody thought of it before, but over the last couple of years, there's been, well, the beginning of quite a lot of work on that particular issue. So, what have we got? We've got a problem that is very, very rare, certainly on human timescales. It's rare enough for really nobody to have any recollection of a major impact event, which is a good thing because it doesn't happen very often. But it's a very bad thing because people can say, well, I've never seen it on the news, therefore it doesn't exist. Trust me, that's how life works these days. When it happens, note when, not if, when it happens, there is no upper limit to the amount of damage an impact event can do. With things like volcanoes, earthquakes, tidal waves, there is a theoretical upper limit on the amount of energy you can dump into the environment. With this, there is no upper limit. But unlike earthquakes, volcanoes, tsunamis, this one is avoidable. This is the one major natural hazard we know how to fix. Maybe rare, but if you stack that up with the possibility of a mass extinction event, but we can fix this one. And, to be honest, it doesn't cost a lot. The international community over the last 25 years has gone from, oh, that's all down with little green men and flying saucers, up to really proper science. The world has woken up, but not everywhere. Back in 2001, some of us made ourselves unbelievably unpopular amongst the politicians by raising this issue, to the extent they set up a task force to look at the whole thing. It produced a report after a year, 14 recommendations. Yay! Not one of them has been implemented. Not a single near-Earth object has been discovered or characterised by a UK-funded telescope. Absolutely true. The UK government did fund a National Near-Earth Object Information Centre, which promptly closed down because they weren't given any money. The current Near-Earth Object Information Centre is unfunded. And in the UK, the near-Earth object hazard isn't recognised as a threat at all. So the UK is sadly a little bit behind. We are a complete non-player in this field. The best way that the UK could help is with the search. If we can't find them, all the rest of it is a little bit irrelevant. What we desperately need are search assets, telescopes. Best would be 4 of these Pan-STARRS-type telescopes dotted around the world. Unfortunately, that's not going to happen. This is the government's view. This does not appear on the National Risk Register. This is held by the Cabinet Office, but it only looks 5 years ahead. So this will never be on the National Risk Register. If you're not on that list, no funding in the UK. Which is a bit of a shame because it's not expensive. If you'll hang in with me, just some simple cost comparisons. Cost of Brexit to the UK economy so far, £76 billion. Thanks to the ones who voted for it. UK spent on confectionery. I couldn't get numbers for 2024, so you'll have to live with 23, £13.9 billion. One single F-35 Lightning aircraft, £215 million. Department of Work and Pensions annual stationery budget, £66 million. And that network of 4 Pan-STARRS-type telescopes, 64. This is what Sir Crispin Tickell, the late Sir Crispin Tickell, described as a rounding up figure. But, sadly, not going to happen. So I've changed the title a little bit. Is the UK smarter than the dinosaurs? Sadly, probably not. However, there are a number of people of questionable sanity, I have to say, who have taken this problem on. This is where I live. Until quite recently, we've been involved in the tracking of asteroids that have been discovered elsewhere using a reasonable-sized telescope and producing observations on just over 13,000 asteroids over the last 20 years. But we've never had a search capability until now. Well, I say now, hopefully within the next year or so. For the last 15 years, my group of volunteers have been working on building a dome and refurbishing quite a large telescope, 24-inch camera, which was given to us by the Institute of Astronomy in Cambridge. This will be a smashing search telescope. Not quite there yet. Not quite. But the best guess in the crew of which these are some. And I don't apologise for the age. We're all geriatrics, and we're all going to be geriatrics, whether we like it or not. But the best guess is that this thing should be up and running within the next 12 to 18 months. So, something is happening in the UK. But I have to say, this all funded by a little box in the shop that we have up at the Space Guard Centre. That is a national disgrace. However, United States, all the other countries in Europe, Australia, Far East, all battling on, and actually I now basically leave this field reasonably confident now that this is a problem that we've at least got in hand. Probably haven't solved it, well, we certainly haven't solved it, but at least the whole problem is being studied, discussed, solutions come up with, and even hardware being produced. So, 25 years ago, we were completely defenseless. Now, at least we've got a standing chance. I'm done. Have we got time for a few?
Well, so the